Thank you, John. So, and also I want to thank all the organizers for this very nice workshop. And I think it's very interesting to meet, these two different communities. So I think it will be very fruitful in the end. So, okay, so in this talk, I want to focus on tensor product structures, and especially local tensor product structures, such that, to build in some adaptivity in, spline spaces, but don't, lose completely the connection with tensor product structures. So that somehow connects a bit with, the talk of you. And okay, I'm not so interested in spline basis functions which are orthogonal and come from the spline community. So I'm interested in basis functions which has B-spline properties, so which look very similar or have similar properties to the univariate B-splines. But since we are still in a tensor product setting, local tensor product setting, univariate B-splines are still very important, and actually the key ingredient in in my talk as well. So that's why I'm very happy that yesterday we had very good introductory talks on univariate B-splines. So I will build further on that. Okay, so basically what I will see is I will start with maybe recalling a bit univariate B-splines and move to tensor product B-splines, and then basically go beyond. So why tensor product B-splines might not be the end of the story, because sometimes you want to have some local refinement. So we want to build in some adaptivity in the spaces, and one possibility are so-called hierarchical splines. So I will discuss what they are, how to build a basis for these spline spaces, and then at the end I will also focus on approximation and how you can build efficient quasi-interpolation schemes in this hierarchical spline setting. Okay, so if you might be interested to know more after this talk, then I can recommend this chapter that I wrote together with Tom and Carla. So it's a bit an introduction to B-splines, spline approximation, and also hierarchical splines. So I think it covers a bit the talks of all three of us in this chapter. Okay, okay. So let me recall a bit what we have seen yesterday, just to refresh our memory. So if you want to define a B-spline, then basically, okay, we need to choose a degree, and we need a knot sequence, a knot vector. That's basically the key ingredient. And we choose n plus p plus 1 knots, because with this choice we can define n B-splines. And okay, I don't know how to get rid of this thing. Okay. So B-splines can be simply defined using a recurrence relation, where we define a B-spline of degree p in terms of two B-splines of degree p minus 1. And basically to start this recurrence, we say a B-spline of degree 0 is simply defined, takes the values 1 on one interval and 0 outside. So that's basically a quite simple definition. And then here you see some pictures of B-splines of different degree. And then they have very nice properties. So here I summarize some important properties. There are many more, but at least this I think is what for me identifies a B-spline. Because also later when I use the term B-spline for other spline settings, and usually I try to mimic this list of properties. So the B-spline has this nice bell-shaped function, so it's non-negative. It has a local support, which might increase with the degree, but not too much. If you look at all the B-splines together of the same degree, you have the partition of unity, so they sum to 1. And we have also nice control about the smoothness. If you remember, this magic formula that the smoothness is degree minus the multiplicity of the knot. And these functions, they are linear independent, so they form a basis for for the piecewise polynomial space, as Carla said. So it's a well-defined space with a given smoothness. And then once we have these bases, we can use them to represent splines in this space, and we know a lot of algorithms to work with them, say to evaluate, to compute derivatives. We have seen knot insertion, so what Tom discussed yesterday as well. And then moreover, say these spaces have nice approximation properties, as we have seen in the talk of Carla. And you can also actually build very cheap and good approximating, say, spline that approximates general functions. So this is what we have discussed as well. So basically, in this case, say we choose our coefficients as, say, certain linear functionals, where, say, these functionals can, of course, not be whatever we want. They have to choose them carefully. So often we want them, say, certain locality, only using information from the function f on the local spot, because that makes them cheap to compute. Say another very important property is polynomial reproduction. As we have seen yesterday, this is basically the key to arrive at a good approximation order. Because, say, if we can reproduce polynomials of a higher degree, we get, say, a better approximation rate. And sometimes you want also more properties, like, for example, not, say, only polynomial reproduction, but maybe also spline reproduction. So having a projector on the spline space. So having a scheme that basically recovers all the splines in the space, because usually this can be an interesting property as well. And then maybe some other features for different reasons. Okay, yesterday we did not have, say, any example of, say, what could be, say, I mean, because of course it's nice to say, well, I want to have, say, schemes with these properties, but can we also build them? And actually, say, for splines and the B-spline representation, okay, there are plenty of schemes, and say here you see, say, some simple examples. So let me, say, give you, say, a construction that actually works, say, for general degree, and say it works as follows. So for each, say, you pick the B-spline, and then, say, you want to figure out, say, what is the corresponding coefficient. So what do you do is, say, you choose a knot in the local, say, interval support of the B-spline, and then, say, you pick p plus 1 distinct points. So here, okay, I elaborated it for degree 2, but of course it works in general. And you choose these points in that specific knot interval. And then, say, we set up, say, an interpolation system. So we say, well, we want to, say, find the spline representation that exactly interpolates the function values in these p plus 1 points that we have chosen. And thanks to the local support of the B-spline, only p plus 1 of these B-splines will be non-zero in that interval. So what do we see? We have, say, p plus 1 coefficient to determine. We have, say, enough data, so it's a linear system of size p plus 1, so we can solve it. And then we get, say, p plus 1 coefficients in this representation. And then what do we do is, since we have chosen a knot interval in the support of our original B-spline, of course, this B-spline must be part of these p plus 1 B-splines. So we take, say, that coefficient that is in front of, say, this B-spline, and that will be the coefficient in our quasi-interpolation scheme. And if we do something similar, say, for all the B-splines, we get, say, a set of coefficients, and that will guarantee that we will get a spline projector. So this is a scheme that will reproduce all splines in our spline space. So, okay, so that's, say, to give an example, say, how you can, say, compute such a good quasi-interpolation scheme. Maybe if you like to have something more, say, explicit, say, here is, say, a formula for degree 2, where we say, okay, we compute the lambda j as just, say, this thing. So we take data from 2 knots and from the midpoints, and that's it. So we see very simple. So we can basically, there exists plenty of good schemes that basically guarantees us, say, these nice properties. Okay, so that's, say, the univariate setting. So we know basically everything about that. So now we want to move, say, to higher dimensions. So what do? We have this very nice framework in the univariate case. We want to reuse it somehow. And the easiest way to move to higher dimensions, we already have seen it before, for example, in the talk of Chris, use tensor product structures because so what does it mean? Say for each dimension, we choose a degree, we choose a knot vector, and then somehow we put these these knots in the right direction. We connect all these things. We get a regular grid, and then we consider a spline space on this regular mesh. And then how do we construct B-splines on a grid like that? Well, we have B-spline defined in the X direction. We have B-splines defined in the Y direction. So our bivariate B-splines are just obtained as a product of one B-spline in the X direction and one B-spline in the Y direction. So that's very simple. Somehow it cannot be simpler than that. And what is very nice is this is not only a very simple construction, but you basically get all the same properties for free in the bivariate setting. So you preserve non-negativity, partition of unity, local support, blah, 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 everything that I mentioned before. So we get it for free. And then okay, we can also use these bases to represent splines in the spline space. And also we get good approximation, because we can exploit again this tensor product structure. So for example, we can build a cheap quasi-interpolation scheme in the following way. So we choose a quasi-interpolation scheme in the X direction, a quasi-interpolation scheme in the Y direction, with very nice properties that we have seen before. And then we do a repeated application of this of these linear functionals, where okay, maybe this might be a bit of a strange notation, but when you apply a univariate functional to bivariate function, then basically it means you freeze one variable, and then you apply it on the variable of interest. So in this way, basically you can again recycle all our knowledge about quasi-interpolation schemes, apply it directly in the bivariate setting, and we get again a preservation of all the properties. So if you had locality before, you have locality here. If you have polynomial reproduction before, you will get polynomial reproduction here, etc., etc. So that's nice. So basically we can say that's it. So that's our bivariate framework, and of course you can apply it also to any dimension. Just take for each dimension again another spline space, and we have a framework in any dimension which is very cheap to use. We have very nice properties, and basically we get the whole package. So then the question is, okay, why we don't stop here? Because actually they are very nice, but they have restrictions, because they are defined on a regular grid, and maybe a regular grid is not always the best grid to work with, especially when you might have functions which has some local local difficulties. So for example, a simple example is you assume we start from a tensor grid like that. We have built a spline approximation on this grid. We look at our approximation, and somehow we see that in the blue area our approximation is not good enough, or some error indicator tells us, look, that's not so good. So what do we want to do is somehow increase our degrees of freedom in that area. But if we are stuck to tensor product grids, then somehow okay, also as Chris said, somehow you can extend the grid, and then you get something like that, which is basically looks like a global refined grid in this particular case. So if you then build tensor, so you get basically an explosion of your dimension. So it's much larger than what you really want. So you would like to have something like this. So that's why somehow a lot of research went into building adaptive splines where you can do local refinement. And there exists a zoo of different spline techniques. For example, splines on triangulation, as what Tanya was mentioning yesterday as well. This is basically a perfect tool for including adaptivity. But sometimes you don't want to completely give up, say, tensor product structures. So, so that's why I say hierarchical splines could be an alternative, which are basically based on tensor product structures. And it has a very nice features. Okay, it's not a perfect solution. There are many more. For example, on Thursday, I think Francesco will speak about LR splines, which is another strategy. But at least say we get some nice features using hierarchical splines, because we get, say, this locality. We can apply it, say, we have full flexibility. So we can use any degree, any smoothness, any dimension. So usually with all these specific techniques, you have to restrict on something. Moreover, we can build, say, good basis function with B-spline properties. And we also know how to build good and cheap quasi-interplans in this space. So we can get good approximation as well in a cheap way. Because that's often, say, a bit of trouble, say, with all these, say, adaptive spline spaces, that they might be complicated to work with. So somehow you want to keep things as somehow still reasonably cheap. Of course, you have to pay a price. That's clear. Okay, so let me start, say, with, say, one of the early work, and I think so. This is, say, a picture taken from, say, a papers of Forci and Bartels from '88, and they basically introduced the hierarchical model, spline model in computer graphics, because, say, they had the idea that, say, if you want to model, say, an object with local features, we don't want to, say, use a very fine spline space. So what do we do is they start with modeling, say, a very coarse, say, rough approximation of the model they have in mind. So using a coarse tensor product B-splines. And then they basically model separately, say, features in a fine spline space. And somehow they just add them on top of the original model. And then in this way, you get, say, you can achieve some kind of dragon model in a cheap way. So anyway, you just use, say, you adapt your degrees of freedom at the place where you want, say, these local features matched. Okay, so that's somehow say, the framework. You go for, say, different levels of resolution, and then somehow you pick the right resolution according to the need at, say, the local space. Okay, but then, say, we want to make this, say, a bit more, say, theoretically founded. So can we, say, also, say, build a basis for a space like that? Because somehow they were just combining different, say, tensor product splines together, and then, okay, you get some nice model. But if you want to use these for analysis, maybe you want a better representation. And then Kraft in his thesis in '97, he proposed, say, the following solution. So basically, to arrive at his construction of say, B-spline basis function in this hierarchical setting, you basically need two main ingredients. So first of all, you select, say, a sequence of nested spline spaces. So, okay, let us say we take L nested spaces from, say, coarse to fine. And then since, say, these spaces, say, we take them as tensor product spline spaces. So we know for each of these spaces a tensor product B-spline basis. So say we denote it by, say, BL. And for simplicity, I will just go for, say, a single index, because anyway, you can always, say, enumerate all the basis functions in a linear way. So in this way, I can explain everything without focusing too much on the dimension of the problem. So in the end, this does not, it's just cumbersome otherwise. So that's, say, is the first ingredient. So we need, say, different spaces of different resolution. And then the second ingredient is somehow you must be able to tell where you want to activate some of the spaces. So we define a sequence of domains, say omega 1 up to omega L, which are again nested, but say in the other direction, where we say, okay, say we would like to activate, say, the space SL in the region omega L. And basically, okay, so the only requirement is that these things are nested. They do not have to look as nice as my picture here, so somehow they can be disconnected, but at least you need some kind of nestedness. Okay, okay, that's a technicality. So basically, whenever I say support, then it's not say the true support of the function. Basically, I'm just interested in say the region inside omega L, which do not necessarily have to be rectangular, but say I forget about say what happens outside. But say if you have a rectangular domain, the support is the same as before. Okay, and then say the definition of the hierarchical basis goes as follows. So we start say on the coarsest level, and we say, okay, we pick all the B-splines of level 1 that basically have overlap in our area. Yes.
But those domains basically would be always unions of rectangles or something?
Does not need to be. I mean, in practice, you choose them as a union of rectangles, but basically the construction goes, you can go for general potato-shaped domains. In the end, somehow the meshes that you will obtain will somehow rectangulize the things, but say for the definition, it does not matter. That's exactly also why I go for this say special support operator, because somehow this allows you to even choose omega 1 as a general thing. The only restriction is that somehow all the spaces must be defined on the rectangle that contains everything. Okay, so I start to say we're taking all the basis functions of the first level that somehow have support on omega 1. And then I go for, say, recursive definition, where I go over all the levels and I update my set of functions. And this update goes as follows. So first, I say, look the set that I have built so far. And I basically select most of this function, but not all of them. So basically what I'm saying is, say, from my previous set, I pick, say, all the functions whose support is not completely in omega L. So it can overlap, but if it is completely in omega L, then I throw it away. So that, say, is the first part of the set. And then I take a second set, which are basically basis functions from level L. And I take only those basis functions whose support is completely inside the set omega L. And then I merge these two sets together, and that will be my new set attached to level L. And I repeat this procedure till I arrive at the finest level that I want, and that's my set of hierarchical B-splines. Okay, so you can, okay, it's a basis. You can prove that this thing is linear independent. But okay, I will not go into that. Just let me say illustrate with an example in 1D. Okay, maybe this hierarchical setting does not make too much sense in 1D because we have univariate B-splines, but this is easier to grasp the idea. So assume we have, say, some mesh like this. And then say, if you look at that, we say, okay, look, we have some refined area, so maybe it's better to split it into levels. So okay, okay, I take, say, that's my first level. Say here I have my final level. So I choose, say, two spaces and two sets of basis functions like that. Okay, somehow I did not plot all the border functions, but somehow you can, I mean, it does not matter what happens, say, outside. So from the first level, I basically select all the functions whose support is not completely inside, say, this region here. And here I basically have one gray function which is completely inside, so I throw it away. And then, say, of my second level, I select also only the functions which are completely supported there. And then what I do, I just throw all these things together, and that's a basis. That's a basis for my space. Okay, so what do we have learned so far? Is say, okay, so if we go for, say, this kind of hierarchical setting, it's clear that, say, we have some kind of adaptivity, some local model, because we choose exactly where we want to have, say, the right resolution. I did not put any assumption on the spline spaces, so I can basically choose any spline space I want. The only restriction was that I have, say, this nestedness. So actually, I can also go use spline spaces beyond tensor product splines. If you want, you can apply this also, say, using splines on triangulations. Okay, maybe you don't need to do it, but the framework is general. And then, say, with say this mechanism of Kraft, I get the basis. So these functions are linear independent. But then, say, if I go over my bullet of properties that I like to have, local support, okay, yes, they are there. So somehow the support depends on the space you want, but it remains local. Non-negativity I have, because they are just plain tensor product B-splines, just coming from different levels, but they are there. But that's basically where the list ends. I don't have partition of unity, which is somehow in the context of, say, geometric modeling is a very precious property, and I don't have this. So maybe, yes.
But this nested domains are somehow not addressed yet. I mean, how do you choose them?
This is, say, a parameter in the setting, so you can choose them as you want. So in practice, basically it depends on the problem, and basically it say you start with something coarse, and then you say where you see error, you start to refine. Yes, in a sense, this framework requires this as input. It's like with, say, the tensor product B splines, the knots must be given as input, and somehow you must find a good way to determine these knots. Once you have the knots, once you have, say, these domains, the thing runs down. But it's of course a very important practical question. But I will not say anything about that, because then this is very, very complicated stuff. Yes. Yes. No, but I will come to that point later. And actually, say, I will also come to the point to partition of unity. So I will recover it. But basically, these spaces have good approximation. But I still am only halfway, so there's still a lot to tell about this. Okay, don't worry, it goes. So then, say, okay, since I have a good basis, but this does not have, say, the full list. So then, say, we were thinking, can we find something better that preserves, say, all the properties we have and gets also the rest, so that we get the full picture. And that's basically the key will be truncation. So how does it work? So first of all, I have to, say, define what is truncation. It's fairly simple. So first of all, I have to, say, tell you something about, say, subdivision, or basically it's some kind of knot assertion. So we know, let's say, if you have a space, say, some function in, say, a space of level L-1, since, say, the spaces are nested, of course, this function also lives in the space of level L, or any space with a higher index. And so I can represent this function in terms of, say, the finer basis functions, because of course any function in the space you can represent. So for example, if I take, say, this basis function, and say the finer space is obtained by just injecting one knot in each interval, then say the corresponding coefficients are here. In this particular case, it's uniform, so everything is quite simple. I get, say, 1/4, 3/4, 3/4, 1/4. And actually, that's a property that you can prove in general. Say, if you represent, say, a B-spline in terms of, say, a finer level, the coefficients will always be, say, non-negative. But say that's basically okay. So apart from this non-negativity, we can do it. And then truncation is defined as follows. So basically, we look at this sum, but we don't take all the terms in this sum. We now look at, say, our, say, domain omega L, and we say, if the B-spline is completely inside omega L, discard the corresponding term and only remain, say the other terms. So that's say what I call if I truncate the spline at level L. So basically, I represent it in say the new set of basis function, and then I throw away some guys that whose support is inside say level L. Okay, so then say with this in overhead, we can say define the truncated B-splines. And actually the definition is exactly the same as before, with the only difference is that I apply this truncation somewhere in the middle of this and this definition. So let me say quickly repeat. So I start say with level L, take all the B-splines of that level, and then say I go over all the levels, update my set as follows. So I go from say the previous set, I look for say all the functions from that set whose support is not completely inside omega L. And I don't stop there, I also apply this truncation operator at level L. So that will be, say, the update of the previous function. And then I just add, say, the same function of level L as before, the ones that are supported in omega L. And then I repeat that procedure till I arrive at the finest level. And that's it. That's is my new set of functions, which I call truncated, hierarchical truncated B-splines. So I just apply this extra truncation. Okay, so let us again look at, say, a picture. So here you see the result we arrived before. This is, say, the hierarchical B-splines. So of course, this I have to truncate somewhere, but this truncation will only affect some of these B-splines. Because, say, if the B-splines were too far away from omega L, it will not affect. Only when we have somehow overlap with omega L. And actually, in this example, only 2 B-splines will be affected and somehow will be replaced by these new functions. And basically, you see that, say, I get a new set of functions, which actually span the same space, and somehow they are still non-negative. And that's, say, is not a coincidence. You can prove that, say, these new functions remain non-negative. And the key reason why, say, this is the case is, let me go, if I succeed in going back, is exactly that somehow these coefficients, if you apply this truncation to bases, these coefficients are always positive. So the truncated version of a B-spline remains positive because the B-splines are positive. I multiply with positive coefficients, so I get a positive function. That's somehow the, okay, it's not the full proof, but at least the idea why you preserve non-negativity. Okay, so that's an example in 1D. Okay, so of course more interesting to apply it in higher dimensions. So for example, I build, say, a mesh like that consisting of three levels, and then say my set of truncated functions will look like this. So somehow if I'm, say, far away from, say, the defined region, I get plain tensor product B-splines. If I somehow get closer to the region, you see that, say, this truncation kicks in, and the shape of the B-spline adapts towards the mesh, and you see that you get different shapes. So that's where, say, the B-splines, say, introduced at level, say, the first level, and say these are the ones at the second level, and at the finest level, you just have the plain tensor product B-splines because there's no truncation over there. Yes.
So it is this truncation basically adjusts those splines, these coarser splines to be more.
Yes, exactly. Somehow you incorporate information from the mesh into the basis. That's exactly what the truncation is doing. Sorry. No. I just take, say, the same set as before, and I apply this truncation. So I don't introduce anything else. So everything is just plain tensor product. Okay, so then let us go over, say, some properties. Okay, as I mentioned, they span the same space. Okay, they are non-negative. Somehow you can prove that they are also linear independent, so they are a basis. And of course, because of this truncation, you basically reduce a bit the support. So it was already local, but it gets more local. So that's usually always good. Say when you, okay, for example, want to do least squares, somehow the matrix become more sparse. So this is some properties that basically follows directly from the construction. But then say we have more, and say one very technical problem, so property, but actually it's a key to many other features, is what say what we call preservation of coefficients. And basically it's say the idea is that so I have my truncated basis. I have a representation in terms of my truncated basis, but I want to connect it somehow to standard plane tensor product B-spline representation, because I know a lot of information about tensor product B-spline basis. So I have a lot of algorithms for that. So thanks to this preservation of coefficients, I can somehow say use what I know for tensor products towards this hierarchical setting. That's basically the key feature of this preservation of coefficients. So technically, say it goes like that. So say assume you have a spline in the hierarchical space. So you can say represent it in terms of my truncated basis. So I write it something like that. So I take a sum over the levels, then a sum over the selected indices that I took in the construction, say in the hierarchical space, and then okay, truncate. But that's the representation I get. And then say if I restrict this function over the area omega L minus omega L plus 1. So basically the strip that is only affected by level L, that does not see level L plus 1. This if I restrict to this strip, my spline I can also represent in terms of standard tensor product B splines of level L, because somehow as long as you don't use function of higher level, since I have nestedness, the rest I can represent as B splines of level L. And then somehow if I have these two representations, then basically I can say that if I look at the coefficients here connected to a certain level, say level L, then these coefficients will be exactly the same as the corresponding coefficients over there. Because of course here I have many more coefficients than of level L than here, because this is just a subset. But the ones that are in my hierarchical setting, well, they are all the same. They must be the same, because if you represent the same thing. So that's the idea. And then some trivial properties from that is basically you get automatically that my truncated basis forms a partition of unity. So because why? If my function is 1, I know that if I represent 1 in terms of B splines, the coefficients must be 1. And so I transfer the ones to my truncated basis. And so the sum of the truncated functions must also be 1. And then you can also look for other known specific coefficients like refilapsis that you have seen in modeling. Basically, you can just pick them from the standard. Okay. So now, we have this setting. So we have a hierarchical space which allows to do adaptivity. I somehow have a good basis which has the properties that yes.
Yeah, we are trying to understand those truncated splines. So you suppose that I will take all the mesh refined force together and build the splines. Aren't those splines?
I'm not sure I understand the question. So.
The levels of the
yes.
So you put them together. You don't treat them separately. You build splines on the combined knots. Is this exactly the same?
So in 1D maybe yes. Okay. In 2D of course not, because that's the whole purpose is higher dimension. Because okay, yes, in 1D somehow yes, then there is no reason to use these in 1D because you have univariate splines on non-uniform knots, and they are the best you can do. So for sure there is nothing to do there. The key point is you want locality in higher dimension and get rid of this global tensor product structure. Okay. So now I want to build, say, quasi-interpolation schemes in these hierarchical spaces. So, and then somehow the idea is, say, if I say use this representation in terms of truncated hierarchical basis functions, then maybe I can come up with a good scheme, because actually I have all these nice properties. So I have the convex partition of unity, which basically, okay, is a nice property anyway for a basis, because usually it's a numerical stable basis. So for computing these things, you should not worry too much. If you use other types of basis functions, then numerical stability is always an issue. So you have small support. So if you somehow that usually indicates locality. So that's also good representation. And then say the preservation of coefficient. That's actually will be my key property that will allow me to build an easy construction for a good quasi-interpolation scheme. So now let me say tell you the solution. So we have, say, again, all this information available for tensor product splines. So we want to recycle these things. So okay, so the construction works, say, I have my L tensor product spline spaces, and I assume I know, say, a very good quasi-interpolation scheme for each of these spline spaces. So anything you can take your favorite function, because we have so many of them. And we know that basically they're all, or a lot of them are good. So you pick your favorite, say, quasi-interpolation scheme for each level. And then I combine them together to build, say, a hierarchical quasi-interpolation scheme as follows. So again, I say my double sum with my truncated function, and then I have to pick, say, my coefficients. How do I pick, say, the coefficients? Well, I say look at, say, my index. So I say if I arrive at, say, level k, I say, well, I want to pick something from my level k there. Then my index j also corresponds to a j in my basis of level L. And then I simply say, well, I have detected, say, the corresponding basis between this one and one of these. I pick the corresponding functional, the corresponding coefficient. And that, say, is my proposal for a quasi-interpolation scheme in this hierarchical setting. So I don't compute anything new. I start from, say, quasi-interpolation schemes for each level, and then I just pick the right coefficients, put them together, and that gives me a new function. Of course, you can always do it. The question is, does it work? And the answer is yes, because, say, what do we want? Say, what is a good quasi-interpolation scheme? So if we go over the list of properties, somehow you must have locality. Okay, that's there because the original functions were assumed to be local. Second property is preservation of, or say, reproduction of polynomials. That's a key property for showing approximation. And well, you can say that if you have chosen, say, quasi-interpolation schemes for each of the levels, such that they reproduce polynomials of a certain degree, then automatically my hierarchical QE will reproduce the same polynomials. And actually the proof is one line, because it follows immediately from, again, preservation of coefficient. Because if you represent this polynomial in terms of these, then the coefficients must match. And since I choose exactly my quasi-interpolant by picking the right choices, I reproduce the polynomial. So basically, I get, say, for free, good approximation, because I reproduce polynomials, and basically that indicates that the order is fine. If you want, say, something more, which is in some contexts important, say if you want also, say spline reproduction, so if you have a scheme that reproduces all the splines in the hierarchical spline space, then okay, you have to do a bit more. So of course, it's a very natural request that, of course, the starting quasi-interpolants must already be spline projectors for their plain tensor product spaces. Of course, no hope otherwise. But then I put, say, an extra condition that, say, the functionals have to use local information, only information from, say, this strip omega L minus omega L plus 1. If I do that, then I get also, say, a reproduction of spline spaces. Okay. If I don't do that, maybe you can still have spline reproduction, but it's not guaranteed. So it's just a sufficient condition. So that basically gives me, say, a framework that where I can, in a very cheap way, I don't have to design new rules. I just take rules that I have and I combine them, and I get, say, good approximation properties. Okay, then of course, if you have, say, a projector, you get also dual basis. That's quite trivial. And then actually you can also prove that basically you get, say, the good approximation order as for standard splines. So this is a formula that basically looks very, very similar to what you have seen in the presentation of Carla. Just here, I say localize it a bit, because now, since I have different resolution, I don't want to take, say, the largest size, because then somehow I always end up with the coarsest mesh. So you want to look locally and hopefully recover locally what happens. So this is more or less the same information. And then you get something like that. So before you had, say, h to the power p plus 1. Here, okay, you have to be a bit more careful and look, say, at the diameter of a slightly larger area, which depends on the supports of say, all the overlapping B-splines on that truncated B-splines on that cell. But okay, but somehow you can control this size. I did not want to write it as, say, in terms of the length of this epsilon thing, but anyway, you can also do that. And then, say, the last thing I want to say is just show, say, a very simple example to show that these things also work. So, okay, let us go for, say, biquadratic tensor product B-splines. So I have to choose, say, a QI for each of these spaces. So I take something that I showed you before, just in a tensor product setting. I do some local interpolation. Now I go for 9 points, because I have, of course, a bivariate setting. And then the same, the trick is the same. I solve, say, local interpolation problem and then pick the right coefficient. So that's, say, is my scheme. And then once I have, say, all these L, say, tensor product schemes, I plug them together and I get, say, my hierarchical scheme. So nothing very, very complicated. And then, say, assume I, say, apply it to a function with 3 peaks. Of course, I need some kind of function which has some locality, otherwise there's no reason to do it. So I choose a mesh like that. So, okay, this was a bit tweaked to mimic, say, the mesh so that it mimics, say, the shape of my functions. And then, say, you get some kind of error plots like that. So if you would not do anything, say, the error goes down. So this is, say, the dimension of the space, the number of degrees of freedom. This is the error. So this is if you would just go for a plain tensor product space on the fine grid. And then, say, if you choose, say, the right say, local spaces properly, you get, say, you can get really a big reduction. And of course, say, okay, I just stopped after a few steps, but you see somehow the trend. And of course, if you would do it in higher dimension, then you might even get more, because somehow tensor product splines blow up quickly. Yes. Okay, I think here in this example, I choose it manually because I have this nice symmetry, but you can also do it with some error estimator. So you can automatically choose the grid starting from something coarse and refine whatever you want. So just the meshes do not look so nice and symmetric. That's the only thing, but say you get more or less the same rates. Okay, so that's basically the end. Say tensor product splines are great because they somehow generalize in higher dimensions in a very easy way. But sometimes if you need to have, say, if you have problems with some local issues, then you want to have some adaptivity. Say one possible way is using this hierarchical model. I mean, there are many other solutions, but it's just one thing. And then say the truncated basis is, say, a nice representation for this space, which allows you to basically get all the properties of univariate B-splines. And especially, I think, this quasi-interpolation construction is very powerful because it's so cheap. Okay, so these were some references that I showed you in the slides, but okay, that's what it is. Okay, that's it. Thank you for your attention.
Thank you, Hendrik, for your presentation.
Yes. Yes.
You have shown that you get the ultimate convergence multivariate when the function is very smooth.
Yes. Yes.
My question is if we can use construct the presentation for functions that have moments of regularity somewhere.
So that's a good question. Say basically, if you look at this kind of a priori estimates, they always assume that you apply it to functions with high smoothness. If the function is not smooth enough, then somehow the estimate does not work. And actually, in these cases, you have to do something special also in the approximation schemes. Say use some kind of special techniques, or at least tune. Say the meshes according to say where you have reduction of yes. So yes, in this context, say the theory does not say anything because you get. I mean, probably you might get say still good trades, but you cannot prove it. 21. This one. So basically, this say this area is nothing else than say you look at say you basically have to look at say all the basis functions that are overlapping say the cell, and then you look at the supports of the corresponding functions, and then the union of this is what you want. So in general, say this thing could be potentially large, but usually we know how to refine the meshes so that these things can be bounded in terms of say the size of this epsilon. In general, not, but we can do it. Yes, this is yes, exactly. I did not mention it. Sorry. So this is this is the infinity knot. Yes, but we can prove something similar also for say for general Q norms. In that case, maybe yes, we might need to assume something on say having some kind of quasi-uniform mesh on each level. But that's fine because say you can even go for say uniform spaces on each level, and then if you're not happy, you just refine. But say yes, we have estimates for general nodes. So.
Questions? Let's thank the speaker once again.